Hi, welcome to part 2 of the road test for the Richtek DC to DC buck converter evaluation board. In part 1 we looked at how well the board performed under DC load characteristics, varying the voltage from its minimum to its maximum, and also for a nominal 12 volt input, sweeping the output current load from minimum up to its maximum 3 amps and beyond. And it performed pretty good. But what we hadn't done is tested the dynamic response. It's claimed in its documentation to have a rapid response to transient load changes. So what we're going to do now is hook it up to the signal generator with the DC load and see how well it lives up to its claims. What I'm going to do is sweep the current starting with a square wave and switching it from 1 amp load up to 3 amp load and back to 1 amp again, using a 100 hertz square wave. And then what we'll do is we'll have a look at its response with different waveforms on its input, and then we will try increasing the load from maybe 10% to 100% load as well. And what we'll then do is go on and see with higher frequency transients and maybe some pulse transients as well. There's a bit of a problem with my scope in that it has a quite a high noise threshold on the low end, so you'll have to forgive the fact that there's some noise there. We'll just have to try and work around that by looking at what noise there is with everything turned off, and then when we turn everything on we'll just have to adjust for that. So starting with the 33622A arbitrary waveform generator, what I've got is I've got a frequency set to 100 hertz. I've got the high level output of the square wave set to 3.890 volts and the low level set to 3.340 volts. Now the reason I've picked these two values is because this low value going into the MOSFET DC load represents exactly 1 amp of output from the Richtek buck converter, and the 3.890 volts represents 3 amps output. So this with a square wave will pretty much exactly sweep us between the positive and negative limits that we want to test this with. What I'm going to have connected up to it is my Agilent meter, so it will read the average. So if everything's working correctly, it should be showing us 200 millivolts across our 0.1 ohm precision sense resistor, which is over here on the DC load. Right here it is a 0.1 ohm 1% sense resistor. The power supply is going to be set to a nominal of 12 volts, which is its normal input for the DC to DC converter, and the scope is going to be monitoring the voltage output. Now as you can see here, it's set to 20 millivolts per division, and even though my power supply is turned off and the output of my signal generator is also off, you can see I've got a lot of noise here, so apologies for that. But if we try and just see through the noise, I've got bandwidth limiting turned on, but unfortunately it's not very good. Even if I take the input and connect it to ground. All right, I'm just touching this on ground right now. You can see that there's a lot of noise at the low end of this. It's not a very good oscilloscope, but it should be good enough to show us what we need to do. All right, so I'm just going to connect that back up to the output. The channel 2 of the oscilloscope is actually connected to the output of the arbitrary waveform generator, so we can see where we want to look for where we would expect to see spikes from the output if the load was causing the output to dip very much. I've set the oscilloscope to AC coupling, so what I'm going to do now is I'll turn on the DC power supply, and because the load generator here, right, so right now we're still reading 0 volts on our meter, and if I go to the arbitrary waveform generator, if I just for the moment pick DC, you'll see it's set for 3.615 volts, and if I turn the output on, you'll see down on the meter here It's currently reading 1.9 amps. So if I actually crank this down, go to the parameters, offset, I'm going to bring this down right now till it reads 100 milliamps. 100 millivolts, which actually will represent exactly 1 amp flowing through the DC load. All right, so okay, so that's pretty much exactly 1 amp there. And as you can see up on the DC load here, if I zoom in a little bit, 3.346 volts. Okay, so that is currently representing 1 amp. So I'll just write that down, 3.346. And if I now increase this so that we get 3 amps on the meter, get the right meter, there we go. So we have the high end of our DC. So we're just doing this with a DC voltage on the gate of the MOSFET right now so that we can just find out where our limits lie. So that's pretty much close enough right there. So that's 3.884 volt on for the high side. Okay, so now let's just go back to the arbitrary waveform generator, and what we're going to do here is we're going to set up the waveform to be a square wave, and we're going to have the high level to be the 3.884. Alright, so we're just going to go 3.884 volts for high, and for the low level we're going to set 3.350, so 3.350 volts. And that's our square wave now that's going out in the arbitrary waveform generator. And if you now look at the multimeter, you'll see that it's reading, it's just marginally off, but it's basically reading 2 amps, which is of course an average reading because we're switching between 1 amp and 3 amps at 100 hertz. So the meter is going to quite happily give us the average reading. Now if we go up to the oscilloscope, all right, you can see the waveform that's coming out here. If I just turn off the output of the waveform generator for a moment, you'll see that there's a little bit of, you can see the gate voltage turning on up here, switching between the two limits. But when I turn the output of the waveform generator off, really the yellow line, which represents the voltage AC coupled at 20 millivolts per division, isn't really changing much. It's just about the same noise. So currently this is not having any effect on it. Now if I turn the output of the power supply off, so we shut it off completely, you'll see that there is a little bit less noise on the oscilloscope on the yellow trace. If you ignore the spikes on the outside and just look at the inner edge, you'll see that it's 20 millivolts per division, so there's probably about 10 millivolts of high frequency noise here. I don't know if I can change the acquisition from sampling maybe to average, just to try and get rid of some of that. So if I turn this off, you can see the noise is a bit thicker than like 5 millivolts. And if I turn it on, there's a little bit of noise there, but it really, increase in noise, but it really hasn't increased at all in amplitude. We're just averaging here. But because it's noise, it's, the average, it's going to average out. What we're actually going to be looking for here is when this ramps up, because this is the 12 volt output, I would expect to see a pulse coming down here and then a pulse coming up here when the transients of this output switches on and off. But it's right now it's not, which is actually good because that means that it is really responding very nicely to the change in output load. Now if I switch back to the arbitrary waveform generator here, just to show you, sorry, before I do that, this is the board here. So what you can see is this is the input from the DC power supply. I've got the voltmeter, a voltmeter connected here, but it's not turned on right now. The oscilloscope is connected directly against the output pin in the ground here, and I'm monitoring the gate on this pin here, which is being driven from the signal generator. All right. Now I have tried disconnecting some of this wiring and just sorting it out, and I can reduce the noise by a little bit. So part of it is because of these scope probes. They just came with the A10 oscilloscope that I have, but you know, I don't have anything better right now to use, so we'll just have to go with that. So let's just go back up to the arbitrary waveform generator here a second. And what I'm going to do now is I'm going to start increasing the frequency of this. Well, actually no, I'll leave this frequency alone for the moment. I'll change it to a pulse output to see if that makes any difference. So I'm going to just go between pulses and square waves. So let's just take you back to the oscilloscope so you can see what's happening here. So this is showing the output again with the square wave. If I change it to a pulse, you'll see the top blue trace change to the pulse, of course, with the averaging. Still can't see any transients on the yellow trace where it's switching between high and low. If I change this acquire to maybe a different, it's just sampling, still can't see any changes there. Peak detector is pretty useless, so it's not showing us any changes there. Now if I change the let's have a look here, waveforms. So that's if I go ramp, all right, there's no detectable changes here. All right, if I just reduce the frequency, reduce the time base slightly. If I change input 1 to be DC coupled, of course, all right, it's off the top of the screen, so I'd have to drop this down to something. The output is about minus 1.05. Oh, I can get it in there. There we go. So you got 20 millivolts per division. Now it's DC coupled, so that's pretty good. So that's a triangular wave going in. Again, it's still sweeping between the 3.35, which represents 1 amp, and 3.8, which represents 3 amps, and I can't see any sign of the triangular wave in that output voltage at 20 millivolts per division. It's doing pretty good. If I change the waveform now, maybe to some random noise, that's just going to put noise in there now. So that really doesn't change anything at all. Nice triangle wave. You know, I just can't see any effect on the output within the limits of what I'm able to measure right now. So what I'm going to do is I'm going to go back to the square wave. Okay, because this is the most likely one to generate any transients. And what I'm going to do is I'm going to change the frequency now. I'm going to start cranking it up. This is at 100 hertz, 200, 300, 400, 500. Now you can start actually to see something happening there. We're at 100 hertz right now. As I start increasing this, you can see the noise. There is some effect there. If I you can just see a slight correlation between some of the noise and things, but I'm not sure how much of that is caused by the oscilloscope versus. All right, so I'm up to 5 kilohertz switching now between 1 amp and 3 amps, and if you look at the meter, we're still, because the meter can run up to about 100 kilohertz input, it's still reading pretty much the 2 amps average that it's supposed to be reading, which is good. And the oscilloscope is still showing us that we have no appreciable noise being added into this. You can actually see a correlation now, just that there is about, and this is going to be purely guessing, maybe a 10 millivolt dip in the output if we ignore any of the superfluous noise that we've got there. I don't know if maybe changing to averaging will make a difference now. Yeah, that's allowing us now to see the actual changes now. It's a little bit better, so you can see these small dips. If I switch this input 1 to AC, it might allow me to get a better reading on it. Oh, I'm at the maximum level anyway, so it's not really making any difference. Yeah, I've lost my DC offset. I'll leave it there now. So that's with a 5 kilohertz input. Let's up it now to maybe 10 kilohertz, 20. Yeah, we're starting to see a small amount of ripple showing up on the oscilloscope. Like I said, it's 20 millivolts per division. So if I put that there, so it's about 10 millivolts of noise that's on that. And I mean, that's some pretty aggressive noise that I'm introducing there. You know, the DC load, it's switching between 1 amp and 3 amps at 30,000 times a second. And it's only introducing a 10 millivolt swing on the output. That's pretty good. Yeah, even taking the, I can't take the bandwidth limit off, of course, on this setting. So you can see that the my DVMM is reading a little bit lower now, but that's probably because it's starting to get towards the end of its bandwidth capability here. The DC load down, sorry, the buck regulator down here, the Richtek, it's not warm at all or anything like that. It's quite happily handling this. So I don't know what else I can test with this thing. It's so far, you know, from a DC response perspective, it's performing pretty good. If I take this back to maybe a pulse waveform, just to try and see if I can make it. So that's a 33 microsecond pulse. So let me just adjust the width, the pulse width. Just trying to make sure I can see this thing, the transient response. So that's a 5 microsecond pulse of 2 amps. So I'm swinging it from 1 amp to 3 amp output for 5 microseconds. Yeah, so 5 microseconds at 20 kilohertz. And you can see the DC output voltage here, it's barely moving anything. The oscilloscope is quite capable of seeing this if it dipped too much. And so, you know, 20 millivolts per division, it's dipping about 5 millivolts, 10 millivolts maybe, not even. I would say that's a wrap. It's not, from what I'm able to throw at it, from, you know, random noise, DC, levels, you know, if I put a sine wave at it, all right, you can see the output there is following it. Now, as I say, that's 20 kilohertz variance of 2 amps. It's following it by maybe 5 millivolts, which is, I think that's pretty good, because the internal oscillator is running at apparently 700 kilohertz. I don't know if I can measure that anywhere. No, there's no pins on that at the moment. I'll have a look at the circuit, but yeah, so that's pretty good. I think from a transient response perspective, this thing is showing that it can do a pretty awesome job. I mean, that's 20 kilohertz. That's a huge amount of high frequency noise that I'm putting on the output of this thing. Normally I wouldn't expect anything quite that high. I mean, if I crank that up in frequency, let's go up something ridiculous. Let's go 100 kilohertz here. All right, there's 100 kilohertz. Let's go up to 300 kilohertz. All right, this thing is still quite happily chucking out the 1.05 volts. If I put my other, I think I've still got my other meter hooked up to measure the voltage. Yep. So if you remember from the first video, it was always outputting about 1.048 volts. So if you go down to the meters, that's the DC output voltage right now, 1.047, which is right on. That's the output current, 1.92 amps. So considering that we're putting out a variance of 300 kilohertz right now, it's pretty much getting out of the range of that. It's just measuring the average. It's doing pretty good. The input to the converter is 12 volts. It's still drawing about 200 milliamps going in and outputting an average of 2 amps going out. And that's what we're inputting into it at the moment, is a 300 kilohertz equal sided triangle wave. So, you know, we've outputted a pulse, we've outputted a square wave, we tried a triangle wave, tried a sine wave, and we've tried noise as well. In all of them, the output on the oscilloscope has remained pretty damn good. So, you know what, I would give that, for any environment that I'm trying to use it for, you know, probably a 10 out of 10. A little bit of extra DC coupling, you know, maybe an inductor on the output to get rid of any transient noises from the Richtek. But as I say, I can't even measure what those transient noises are right now, because you know, if I take the waveform generator back to a DC output, which is what I've just done, as you can see there, it's now sitting at 3.617. So if I up this to read a 3 amps, so 3.88 volts. Alright, so that's a 3 amp output. You can see that the noise that is actually being shown here on channel 1, as I say, I can't increase it anymore. Change the triggering to channel 1. Oops, went too far. See if I can actually get this thing to trigger at all. Yeah, so what I'm actually trying to look at here, if the actual frequency that we're seeing here, this AC, if you look here, this is roughly the 700 kilohertz. It's flicking around a bit because it's got noise in there that's interfering a bit. But basically it's the 700 kilohertz signal. I don't know if I can switch my probe maybe to ×1. It should be okay to do that. So that's ×1. So that's now actually 2 millivolts per division. Let me just try and adjust this so that it reads correct. Alright, so that's 2 millivolts per division. And there. So that seems to be free running at about 790, 780 kilohertz, which is about what the manual says that this thing switches at. So that basically there is your output switching noise, and it's you know, for about 5 millivolts on the output of 1.05 volts. So it doesn't, you know, it represents 0.5% of the output, so that's not too bad at all. Yep. So anyway, that ends of the dynamic load response test of the Richtek. As I said, I think it's still pretty good. If you have any more suggestions of what you want me to try and test with this thing, I'll be happy to do that for you. This is just what I have available to me at the moment. So anyway, give me your comments, give me your feedback, be appreciated, and look forward to the next challenge. Thanks.